So let's solve a system of differential equations where we get complex conjugate eigenvalues. So let's solve x prime equals ax, where a is given by this matrix. So of course we need to find the eigenvalues and the corresponding eigenvectors of a. So we find the determinant of a minus lambda I, given by this expression. Take the determinant, so we'll have 2 minus lambda times negative lambda minus 2 times negative 5. Multiplying this out just gives us lambda squared minus 2 lambda plus 10. Set the characteristic polynomial equal to 0. And let's complete the square. we notice that that's not an easy quadratic to factor. So if we move the 10 to the other side, we take 1/2 of negative 2 to get minus 1. We square it, we get 1. So we add a 1 to both sides. We get a negative 9 on the right-hand side. The left-hand side can be written as lambda minus 1 times lambda minus 1, which is the same as lambda minus 1 squared. Take the square root, get lambda minus 1 is plus or minus 3i. Move the negative 1 to the right-hand side, and here are our eigenvalues. So going back to the notation we've used many times, alpha plus or minus beta I, our alpha is 1, our beta is 3. Now let's find the corresponding eigenvector for the eigenvalue 1 plus 3i. Let's use the positive sign here. That's what we did when we derived the formulas when we talked about this last time. So again, we're replacing lambda here with 1 plus 3i. So we get 2 minus the quantity 1 plus 3i. Here we get minus the quantity 1 plus 3i. Simplifying the first row here, 2 minus 1 gives us 1, and minus 3i. Be very careful with that negative sign. This stays negative 5. I didn't even do anything on the second row here. Now, it doesn't appear that these two rows are constant multiples of one another. It's not obvious, but they are, because the determinant of this matrix is 0. So just pick one of the equations to work with. I pick the first equation. So I get 1 minus 3i times x sub 1 minus 5 times y sub 1 equals 0. Now there's an infinite number of solutions to this equation, and we're just going to find one. So we move the minus 5y to the right-hand side of the equation, and then I just divide by 5. Now, again, there's an infinite number of solutions, so let's pick an x sub 1 to make this as nice as possible. So let's pick 5 for x sub 1. When we do that, the 5's cancel, and your y sub 1 will be 1 minus 3i. So here's our eigenvalue. The first component's 5 because we picked it that way, which made the second component 1 minus 3i. Now we need to get the real and imaginary parts of this eigenvector together. Notice the real parts are 5 and 1. The imaginary part, we need to have a plus sign here. The imaginary part then is 0, negative 3. Because of that negative sign. We want this to be positive, which makes that second component negative 3. So the a and b of the notation we used earlier to derive our solutions are a is 5, 1, our b is 0, negative 3. So let's put our solutions together. This is the first solution that we derived when we were working on this last time. So the first solution is e to the alpha t times the quantity a cosine beta t minus b sine beta t. That's what we derived last time. Now remember, alpha and beta come from your eigenvalue. So alpha's 1, beta's 3. Putting it all together, here's the vector a, your vector b, e to the t because alpha's 1, cosine 3t, sine 3t because beta is 3. You can simplify this, just multiplying through. We get this expression, and then I multiply through by the e to the t out in front to get this expression. Our second solution that we derived last time, the second solution is given by e to the alpha t times the quantity b cosine beta t plus a times the sine of beta t. Again, we know alpha is 1, so we have e to the t. This is our vector b. This is our vector a. And we can just multiply it out to get these expressions. So we have two solutions. We find our general solution by taking the linear combination of those two solutions. So we just multiplied the first solution by a constant c sub 1, second solution by the constant c sub 2. This vector is our first solution. This vector is our second solution. You can rewrite that as taking your fundamental matrix times the vector of constants. The first column is your first solution. Your second column is your second solution. That's another way to express it. Now another way to think about it, if we multiply through here, we take the constant c sub 1 times this term plus c sub 2 times this term. That gives you your little x of t, the first component of your solution. The second component of your solution is just the constant c sub 1 times this expression plus c sub 2 times this expression, this longer expression here. But your solution is made up of two different functions, little x of t and little y of t. So you can rewrite it that way too. It's just two different.
Sorry, I don't know that one.